Okay, how's it, Chase? Welcome to another video lesson. Today we're going to be doing section 6.11, continuing with differentiation, and basically we're looking at the function of a function and how to differentiate it. And the rule is called the chain rule. Okay, so the chain rule. Okay, so your book starts off by saying if we wanted to differentiate a function like y is equal to x plus 2 squared. That would be quite easy to differentiate. We could multiply it out, and then we'd end up with ax squared plus bx plus c, and we could differentiate that using the polynomial differentiation rule. We could also just take this and use the product rule, because that's two functions multiplied, right? But what happens if you have something like y equals x plus 2 to the power 8? You do not want to multiply that out at all. No, because that would be a huge mission. So, and to use the product rule for this would also be a massive mission. So what you do here is the chain rule. Okay, so basically let's see how your book describes it. Okay, so how your book describes the chain rule is it, let's write out the formula here. It says dy by dx is equal to dy by du times du by dx. Okay, and I'm going to explain that now, don't worry. So basically what they say is, how can we differentiate this easily? What if we let x plus 2 equal u? Okay, so this is equation 1. Then y equals u to the power 8, right? Because we let x plus 2 equal u, so y equals u to the 8, and that is equation 2. So then if we take, if we want to find dy by dx, we calculate dy by du and du by dx, and we'll have our answer. So let's calculate dy by du. So that would be this equation. So dy by du equals, and we can differentiate, so we're differentiating y with respect to u. We can differentiate this very easily. It's just a polynomial. So what do? We multiply by the power in front, write down our u, and decrease the power. So we've differentiated that. So that's dy by du. Next we need to use du by dx. So we've got u equals x plus 2 du by dx is equal to, and if we differentiate that, what do we end up with? We end up with 1. Okay? And then we've got that done. Okay, we've got du by dx and we've got dy by du. Okay, so therefore by the chain rule, dy by dx is equal to dy by du times du by dx, which is 8u to the 7 times 1. Okay, but now be careful. We need to write this in terms of x, because remember we made a substitution here, and we said u equals x plus 2. So this is the derivative of y with respect to x, so we can't have a u here, so we need to replace this u with what it's equal to in terms of x. So dy by dx is actually equal to 8 x plus 2 to the 7 times 1. So there's your final answer. We just substituted x plus 2 in for u, and there we've got our derivative. Okay, so let's quickly do example 35 and 36. So example 35 says determine the differentiation coefficient. Alright. Basically they say differentiate y equals 3x squared plus 4 to the power of 5. So what happens, do you see that we can differentiate this inside piece? It's easy to differentiate 3x squared plus 4, and it's also easy to differentiate u to the 5. So let's let u equal 3x squared plus 4. That's equation 1. Therefore, y equals u to the 5. So we're just making a little substitution. And then we know by the chain rule that dy by dx is equal to du by dx times dy by du. Okay, and let's do our derivatives. So du by dx of 3x squared plus 4, so that is equal to, this is easy to differentiate, it's just a polynomial, so take 2 down to the front and multiply, that gives 6. Write your x, reduce the power by 1, and the differentiation of a constant is 0. So that's 6x. Then dy by du is equal to, how do we differentiate this? It's just a polynomial. So what do? We take the power down to the front, so 5, write down our u, decrease the power by 1. Okay, and now we know that we just need to multiply them together, these two derivatives, so we get 5u to the 4 times 6x. And remember, we need to substitute in for u because it all needs to be in terms of x. So dy by dx is equal to that, and we just substitute in for u. Dy by dx is equal to 5 times u is 3x squared plus 4 times 6x. And there you go, there's your derivative. You don't have to multiply it out any further. Okay, and example 36. Okay. What if we've got the function y equals root x squared plus 2? I'm just going to write this in a different form. Y equals x squared plus 2 to the half. Right? I haven't changed anything. So once again, can we differentiate u to the half? Yes, we can. It's just a polynomial. Can we differentiate the inside thing? Yes. So we let u equal x squared plus 2, and therefore y equals u to the half, or square root of u, and we go from there. Okay, I just want to do one more. This is from your exercise. 6.14. I just want to do example. Let's do 6. So number 6 says differentiate y equals a to the x squared. Okay. So how can we differentiate that? Well, what if we let u equal a to the x? Then we've just got u squared. So let u equal a to the x, and therefore y equals u squared. See, because we can differentiate a to the x and we can differentiate u squared. So that's what you're looking for. You're looking for forms which you can differentiate. And then you make your substitution so that it's possible, so that those forms exist. So we know that dy by dx equals du by dx times dy by du. Okay? And then we calculate du by dx equals, the derivative of a to the x is a to the x ln a. Just look at your derivative table, you'll see it there. The derivative of u squared is dy by du is equal to 2u. Okay, so now we can multiply those two together by the chain rule. So dy by dx is now equal to 2u times a to the x ln a. And we've got a u here, and remember u is a to the x. So we get a 2 times a to the x times a to the x ln a. And you could leave it like that, but it can be simplified slightly. This becomes 2a to the 2x ln a. And there you go. That's how you use the chain rule. Now at this point I just want to show you a website, show you my competition. If you get stuck with your calculus, because I know calculus is tricky to get hold of and you don't have much time. khanacademy.org, I think it is. Yeah, there you go. So if you go check this out, okay, that's annoying that you have to sign in, but I suppose it's fine. Point being, I just want to show you I want to show you what's available here. Oh my word, they've really upgraded this site and made it annoying, but just go through it. Okay, so we're gonna go here. If you go to calculus, sorry, my internet's decided to be a bit slow tonight. Okay, so taking derivatives, there's a lot of videos available on derivatives, as you can see here. So you can just find what you need, of course. See, there you've got the chain rule and the product rule and so on. So yeah, take a look at this site. It's very good, especially for basic derivatives and integration. Very good site to check out. Like if you haven't grasped onto it through watching these videos and through your studies, then that is definitely the site to go check out. I highly recommend it. Okay, the next section is section 6.12, direction of a curve. Okay, so talking about the direction of a curve. So we know that given a function y equals f of x, then dy by dx is the gradient of a function. Dy by dx can also be expressed as f prime of x equals ... right? So in order to determine the gradient of a function at a point, then we can substitute in an x value, and the derivative will calculate the gradient, right? Because the derivative is also a function. So we can calculate the y, we can calculate the gradient at that point. So, for the example they give in your book is this one over here. And they just give y equals x squared, but only from 0 onwards. So there. And basically, the gradient at any point can be represented by a tangent to the curve. So if I draw in a tangent there, okay, and let's call this point theta, and that is the point 1 over 2, 1 over 4, for example. Okay, this is the function y equals x squared. So, what if we want to know the gradient at this point? Well, dy by dx for this function is going to be equal to 2x. So, dy by dx at point theta equals 2 times 1/2 is equal to 1. Is equal to the gradient at the point 1/2, 1 over 4. So now we know the gradient at that point. We can also give it a, remember that we can also give this line now, this tangent line, an angle of inclination. Okay, so, and that is defined by m equals tan theta. I think you'll remember doing this somewhere. So in this case, we've got 1 equals tan theta. Theta equals tan inverse of 1. And that is going to be equal to 45 degrees. Okay, so there you go. We know that at that exact point, the gradient of the curve is 45 degrees, if you want to express it as an angle. Okay. You can also see on this curve, okay, can you see that the function is positive and increasing for all values of x greater than 0. So if we look from there onwards, you see the function is increasing, and can you see it's concave upwards. Now what I mean by concave upwards is something like that is concave upwards. Something that maybe has a shape like that is concave downwards. You see, so it's basically in which direction is it pointing. See, that's more or less concave upwards, concave downwards. Okay, you get the picture. So this function is concave upwards, positive, and increasing for all values greater than of x greater than 0. Okay, how do we know that it's increasing? The gradient is greater than 0. If the gradient is greater than 0, a function is increasing. If the gradient is less than 0, a function is decreasing. So here they give the example 39 then. Example 39. Okay, consider again y equals x squared with dy by dx equals 2x. Okay, and they give you the graph. Okay, there's our function y equals x squared. They also give you this point. -1/2 and 1 over 4. Okay. And they say, what is the gradient of the curve at the point 0, 0? And I already said, how do we do that? We substitute x into our derivative. So dy by dx equals 2 times 0 at the point 0, 0. So dy by dx equals 0. So the gradient at the point 0, 0 is equal to 0. So what that means is if I drew a tangent line, it would be a constant. It would look like that. Okay. Let's see what else they say. It's clear the turning point of this curve is 0, 0. Okay. So that when the gradient is 0, it represents a turning point, which you can see clearly. It's going down, it's decreasing, decreasing, and then it hits the turning point, then it's increasing, increasing, increasing. Okay. They say we also note that for negative values of x, dy by dx is negative, which you can see if you draw a line like this. You see that it's heading in that direction. So the gradient is negative. And when x becomes positive, do you see that we draw a line like that? Remember, you always draw from left to right. So the gradient becomes positive. So it's negative gradient, then 0 gradient, then positive gradient. Okay. So for values of x less than 0, this graph has a negative gradient, and that means it's decreasing. And then for values of x greater than 0, it has a positive gradient, which means it's increasing. So for all negative x values, which is this half of the graph, the function y equals x squared is concave upwards and decreasing. And then for all positive values, the function is concave upwards and increasing. Okay. The next section is 6.13. 6.13. And this is about finding the equation of tangent to a curve. Okay, finding the equation of a tangent to a curve. And they give you this. Once again, they've given you some form of something that sort of looks like a parabola. And they draw a tangent to a specific point. Ooh, that is not a tangent, sorry. Remember, a tangent touches once and never again. Okay? And they give you this point, P1. So this is a tangent at the point P1. It's a tangent to the white graph at the point P1. Okay? And you can see that a tangent is a straight line, which means that you've got the equation y equals mx plus c, or I think they called it point gradient form, y minus y1 equals m x minus x1. So if I'm given a curve like this white one, excuse me, if I'm given a curve like this white one, how would I find the equation of the tangent to the curve at point P1? Well, you'd have to be given point P1. They'd have to say point P1 equals A and B. Once you know that, do you agree that you've now got this is an x1 value, so that can go in there. You've also got a y1 value, which can go in there. This y and that x stay, and we need m. How do I get m? Well, m is dy by dx at the point P1. So once I calculate m, which is what we were doing in the previous section, I can substitute everything into this equation, and I can solve the equation of the line at the point. So let's quickly do that in example 41. Let's see if I can get it all on, see if I can keep everything on the page here. Okay, did I say equation 41? I meant example 41. Okay. So they say, find the equation of the tangent to the curve y equals x squared at point 1/2, 1/4. Okay. So, to visualize it, here we've been, let me just draw it, I'll draw it nice and small. We're given our graph y equals x squared. Our tangent is at 1/2, 1/4. So it's at this point here somewhere. And we draw a little tangent. Okay. So we've been given a point on the line. So we already know that. So the first thing we're going to try to find is our gradient. So let's do gradient in green. dy by dx is equal to, the derivative of that is 2x. Okay, so dy by dx at the given point, which is 1/2, 1/4, is 2 times x is 1/2, equals 1 at 1/2, 1/4. Okay, so therefore m at that point is equal to 1. And we know that x1 is 1/2, y1 is 1/4. So we just say y minus y1 equals m into x minus x1. Okay, let's start substituting. Y minus y1 equals m, which is 1. So 1 into x minus x1 . Okay, and then we can just solve the equation. So let's do it. Y minus 1/4 equals, the 1 doesn't matter, multiply, it just gives us x minus 1/2. Okay, so y equals x, take this across, it gives minus 1/4. And there you go. You've solved the equation of this tangent here. So that tangent is y equals x minus 1/4. And just in case you didn't believe it, let's test it. So it's going to quickly plot them and see. So our two equations were, I need to go to graphing mode. Now I can't see it for some reason. There we go. Okay. We had y equals x squared as our first one, and y equals x minus 1/4. Okay, graphic. Do you see? Perfect tangent line right there. And if you zoom in on that point, you'll see that the green line only ever touches the blue line once, right over there. You see that? Okay, so there you go. That's how you calculate your tangent line. Okay, next they talk about the maximum and minimum values of a function. So let's do it. 6.14 max and min values of a function. Okay, so let's talk about maximum and minimum values. So let's look at this function. Do you agree that this function has a maximum and a minimum, right? Assuming it looks like that afterwards. It's got a maximum and a minimum. Okay, most functions generally only have one or the other. Okay, so let's consider a negative parabola. Can you see that this function has obviously only got a maximum. It doesn't have a minimum that we can define because it just goes on forever downwards. See that? Okay, so this function has got a maximum. Now one thing you must notice with a function that has a maximum is if we look to the left of that maximum, do you see that the gradient is positive? And then to the right of the maximum, the gradient is negative. Okay, so basically what happens if a function has a maximum, so if a function has a maximum, let's draw a number line here. And remember, you work from left to right, so small x is smaller and then x gets bigger, right? I'm going to draw a couple of points. I don't even want to give it numbers. Okay. But say we know that we have a maximum which is over here. Okay. So this is a maximum. Okay. And we saw previously that to the left of that maximum, the function is increasing. So for all x values here, the function is increasing. So dy by dx is greater than 0. Positive gradient means it's increasing. And then to the right of that maximum, the function is decreasing. Okay, so for all numbers greater than or to the right of the maximum, dy by dx is less than 0. The function is decreasing. You'll also notice, and one thing that I didn't point out, is that at the maximum, the gradient is 0. Okay, so if a function has a maximum, then a function has a maximum if to the left of the turning point, because dy by dx equals 0 is also a turning point. So if to the left of the turning point it is increasing and to the right it is decreasing, then you know we've got a maximum. And then let's quickly look at a minimum. A minimum is going to be the exact opposite way around. So there's a function with a minimum. The minimum is over there. The minimum is also a turning point, as you can see, because it changes direction at the minimum. Okay, if we look to the left of the minimum, do you see that we are decreasing? Function is decreasing, right? Then to the right of the minimum, the function is increasing. Okay, so when we've got a minimum on our number line, okay, our minimum is there. We've still got dy by dx equals 0, and then to the left of that, our function is decreasing. So for all values to the left of the minimum, the function is less than 0. And for all values to the right of the minimum, the function is, or the derivative is positive, because the function is increasing. Okay, so how do we determine whether a function has a maximum or a minimum? Well, we're going to quickly do example 42. And I'm going to try to do it small for you. Example 42. Okay, so they're basically going to say, does this function have a maximum or a minimum? So they say, given y equals minus x squared minus x plus 2, does the function have a maximum or a minimum? Okay, so, and they might ask you for the coordinates of the maximum as well. So how do we determine where the coordinates of the, well, you need the coordinates of the maximum. So how do we find the maximum? Well, we just said dy by dx equals 0. at the maximum. So let's get dy by dx first. Okay, and you should know how to do this by now, so I'm not going to help you with that. Okay, there we've got dy by dx, and we know that at a maximum or a minimum, dy by dx equals 0. So let dy by dx equals 0. So we've got minus 2x minus 1. I'm going to do it in green actually because we're working with the maximum or the turning point. Okay, so let's solve for x. X equals, take that across, negative a half. Okay, solved for x. Okay, now how do we get the corresponding, now we've got the x coordinate of our turning point. We don't know whether it's a maximum or minimum, we just know it's a turning point because dy by dx equals 0 for all turning points, but we don't know whether it's a max or a min just yet. So now we need to find the corresponding y point. So we've got an x value, we substitute it into our original function, and that'll give our corresponding y point on this graph. So let's do that quickly. So y equals minus a half squared minus, that's minus negative a half squared minus negative a half plus 2, which is equal to, you can just pop it into your calculator, that is 2 1/4. 2 1/4. Okay, so now we've got the coordinates of our turning point. Negative a half, negative a half and 2 1/4. Okay, so there is your turning point. Now we need to know if it's a maximum or a minimum. Well, if we look at our timelines, didn't we just say that if we're to the left of our turning point and it's and the derivative is positive, and then to the right of our turning point the derivative is negative, then it's a maximum, and vice versa for a minimum. So what we can do is, if we just substitute in an x value slightly to the left of this x value, which is 1/2, and then another value slightly to the right of this x value into our derivative, and we see the signs of the derivative, then we'll know whether it's a maximum or a minimum. So let's substitute in a value to the left of negative 1/2, and you can choose any value, but choose an easy one. So I'm going to say x equals negative 1. Okay, so let's quickly substitute that into our derivative. I'm running out of space. So if dy by dx equals negative 2x minus 1, and we substitute that in, then we have minus 2, which is equal to 2 minus 1, which is 1. So to the left, dy by dx is greater than 0, because 1 is greater than 0. Then to the right, we need to substitute a value into the derivative to the right of our turning point, to the right of that, and a value to the right of negative a half is 0 if we look at a timeline. So dy by dx equals negative 2x minus 1. We substitute in 0, and we have 0 minus 1 is minus 1. So to the right, dy by dx is less than 0. So now we know where our turning point is. That's the first step. We've checked to the left of our turning point. We've checked to the left of that x value, and we've checked to the right of that x value. And we can see that to the left, dy by dx is positive, and to the right it's negative. So it is obviously a maximum, because a maximum has a positive derivative on the left of the turning point and a negative derivative on the right of the turning point. So therefore the turning point is minus 1/2 and 2 1/4, and it is a minimum. Or no, it's a maximum. I said it's a max. It's a maximum. So there you go. And there's another example, 43, but it's really a very similar thing. Okay, and we're almost at the end of this chapter, which is fantastic. I thought differentiation was going to take a bit longer than this, so at least we get to spend a bit of time on integration, which is actually not that long of a chapter. It's just let's see, yeah, it's about 25 pages. Differentiation was 43, so hopefully we can be done in good time. But anyway, 6.15 is point of inflection. Okay, a point of inflection is basically a point on a curve where it changes from concave upwards to concave downwards. So you need to understand what concave upwards and concave downwards means, and they give the example of a curve here. Do you see that this part of the curve on the left is concave downwards, and the part on the right is concave upwards? Okay, so the point of inflection is the point where it changes from concave downwards to concave upwards, or from concave upwards to concave downwards. So basically when it changes the direction of its concavity, and we'll call that point P. Okay, so basically a point of inflection is kind of like a turning point, but for concavity, which means that if you look at it, do you see that the the gradient is negative because the function is decreasing on the left? Okay, so to the left of this point the gradient is negative, but it's becoming less negative, and then it's becoming more positive afterwards. So basically dy by dx increases before P, or before the point of inflection, and decrease after P, or vice versa. So the derivative of your function will either increase before P and decrease after, or decrease before P and increase after. So what case do we have here? Well, if we think about tangent lines, which is basically our derivative, if we draw a tangent there, I'm using the wrong color here. Let's draw a tangent there, and then we draw one there. Do you see it's the derivative is increasing, it's becoming more steep, and then after the curve, after the point of inflection, it's getting less steep. Okay, so in this case the derivative is increasing and then decreasing. Okay, remember, derivative is slope of the curve, and you can think about it in terms of a tangent line to the curve. Okay, let's just see what they need you to be able to do. Okay, so the most important thing to know about the point of inflection, the point of inflection P is where d squared y by dx squared equals 0. So that means your second derivative, this is your second derivative, or your derivative of your derivative. So how do you calculate that? Because I don't know if we've spoken about that. So if I've got y equals x cubed, dy by dx equals 3x squared. Okay? To get d squared y by dx, I just differentiate the derivative. So d squared y, and the rules all stay the same, by dx squared equals Now differentiate that. So take the 2 down in front, so I get 2 times 3x, decrease the power 1, equals 6x to the 1. Okay, so that is how I get my second derivative. And what they're saying is that the point of inflection is the point where d squared y by dx squared equals 0. So in this case, we would have 6x equals 0, x equals 0. And that would be our point of inflection, is the point where x equals 0. Okay, so I'm going to end off the video by just doing a quick find the point of inflection example. And then we're going to move on to, we're just going to do one last example in chapter 6 before we jump into integration tomorrow. It looks like we're going to have enough time, which is great. So given the function y equals x cubed plus 2x squared plus 5, okay, find the point of inflection, P. Okay, so the point's name is P. So you know that the point of inflection, so point of inflection, actually for the point of inflection, we know d squared y by dx squared equals 0. So let's calculate dy by dx of this function, obviously, is equal to 3x squared plus 4x, yeah, and that's it. So d squared y by dx squared, so our second derivative, is equal to, differentiate this one again, 6x plus 4. Okay, then to get the point of inflection, we know let d squared y by dx equals 0. So for inflection point, okay, 6x plus 4 equals 0, therefore x equals negative 4 over 6 equals negative 2 over 3. Okay, now we've got the x coordinate, but a point P, they want the point of inflection, has an x and a y coordinate. So I take this x coordinate, I substitute it back into my original function, and I'll get the corresponding y coordinate. So we use y equals negative 2 over 3 cubed plus 2 times negative 2 over 3 squared plus 5. And I'm going to calculate this in my head like a retard. Yay. That is negative 8 over 27 plus 8 over 9 plus 5, which is equal to minus 8 over 27. You could just do this on a calculator. I'm just too lazy to go get mine right now. 8 over 27, what's the common base there? 27 times 3. Okay, 8 times 3 is 24. 27 plus, to get that on a base 27, 5 times 27 is, let's check, 5 times 20 equals 100, 5 times 7 equals, 5 times 7 is 35, so 135. So that is going to be 135 over 27. Okay, and we can add that all up. Minus 8, 24. Let's do 24 plus 135 is 159. Yes, 159. Minus 8 is 151. 151 over 27. Feel free to pop that in, that whole thing in your calculator. So we've got our point P. Point P, because we've calculated our x value by getting the second derivative, letting it equal 0. We solved our x value of our point inflection. Then we substitute that x value into our original function, and we calculate the corresponding y value. And that gives us our full point, or both of our coordinates. Okay, and that is point of inflection. Thank you very much for watching. Cheers.